So what we're going to do now is we're going to take a look at another variant of using completable futures in the context of the image stream gang. And this particular approach is going to download, process, and store images asynchronously in a designated thread pool. Rather than using the common fork join pool, we're going to make our own thread pool. And it's going to be a fixed thread pool, just to show another way of doing things. And this will also show off some other cool features as well. So we're going to end up having just a boatload of threads here. We're going to have 100 threads. That's probably overkill. We probably don't need 100 of them. But heck, why not, right? I got a lot of memory on my machine, so it's not going to hurt anything. Then we're also going to define something we call a thread factory. And this particular thread factory is going to make a new thread, and it's going to make that thread a so-called daemon thread. And daemon threads just mean that when the main thread exits, all the daemon threads exit as well. So what that means is when this program is done, the thread pool will also have all of its threads go away as well. We have a constructor, which is going to stash the array of filters and the list of input in the superclass. Don't worry too much about that. Here's the main entry point method into this framework called InitiateStream. We figure out how big we want the thread pool to be, and it's going to be the minimum of the number of filters times the number of images to download, and then S-max threads. So we're going to try not to have more threads than we need. What we're doing here is we're saying if we're going to download 50 images or whatever, then we're going to have 50 threads. If we're going to, and the reason for that is we want to have as many threads as there could be things that would block. We then go ahead and make ourselves a new fixed thread pool with that thread pool size and the thread factory that we created, the thing that was defined up here that makes daemon threads. And that's going to be the executor that'll be used throughout this program. And then we tell the superclass to start all the processing. Well, what the superclass is going to do is it's going to turn around and call process stream, because that's the main entry point into this example program. And now we're going to do some different things than we did before. And this is going to show off some other cool features. So what we're going to do is we're going to take the list of URLs, and in parallel, we're going to go ahead and check to see if those various URLs are already in the cache or not. So this is the same code we saw before. You can see here we go and asynchronously apply the URL cached method to see whether or not we've seen this before. That's what I talked about in the previous example. The executor that gets returned here, of course, is the one that we set, which is going to be the one that's the fixed thread pool example. So we're going to end up here with a stream of completable futures to optional URLs. So that should look very, very much like what we had before. Except now what we're going to do is rather than use collect here, we're going to use a helper method called join all stream. And join all stream is just a little helper method that I wrote that basically does what the finisher method did in our stream of futures collector that we looked at before. So what this basically does is just a standalone way of doing the same thing. We take a stream of completable futures to type T, and we go ahead and we allocate a new array using the completable future array syntax. So we take the future stream and we make that into an array, which is very cool. You can take a stream and turn it into an array. So we have an array of these elements that are in the, we went from a stream of completable futures to type T to an array of completable futures to type T. And then we go ahead and use the allof method on that array. We get back a single completable future. And then when all the things in the stream have finished processing, we do the then apply trick where we convert the stream into basically, we take the futures array, turn it back into a stream, and then we go ahead and map everything and join them. So we end up here with a completable future to a stream of T that will be completed by the time this thing is done. So we end up here basically getting ourselves a stream of these URLs. And notice we don't have optionals anymore, which is great. I take it back. We still have optionals, but we're going to get rid of them here. After this is finished, we then take our stream of completable futures to optional URLs, and we come through here, and then we're going to go ahead and remove all the empty optionals. So at this point, all the empty optionals go away. So we say stream, flat map, optional stream. And so now we've just got a stream of basically URLs. So we have a stream of URLs now, which are the ones that were not cached. So the rest of the code is way simpler than what we did last time because we don't have to deal with those optionals everywhere. So then what we're going to do is we're going to call map to download the images asynchronously. We'll look at that in a second. That'll give us back a stream of completable futures to images that are being downloaded, but not optionals, but images. And then we call flat map on that, passing in the apply filters async call, and that will end up creating a stream of completable futures to images that have been downloaded and are in the process of being processed. So let's go take a look at download image async. This is now way shorter than it was before, way cleaner than it was before because the optionals have gone away. All we do is we say completable future supply async, download image. I think you can guess what download image does. It's just going to go ahead and download the image. And you'll notice we don't use managed blockers here, and that's because we're not using the common fork join pool. Managed blockers only make sense with the common fork join pool. Here we've spawned off a boatload of threads, and so hopefully there's blocking context for them. So we download the image, each image in the thread pool. So we're going to download an image asynchronously. We get back a completable future to an image, not a completable future to an optional image, so it's cleaner. And then we take that stream of completable futures to images, and we flat map them through apply filters async. Apply filters async is very much like we looked at before, except now we've no longer got optionals again. So we take every one of our filters, convert them into a stream. Then for each filter, when the image has been downloaded, we go ahead and asynchronously apply the filter on the image that was downloaded and run that and do that in the fixed sized pool, fixed size thread pool. So that's going to go ahead and run back in the background there. And that, as you can see, like before, returns a stream. It's a stream of completable futures to images, not a stream of completable futures to optional images. So that's a lot cleaner than we saw before. And then we go ahead once again and we use join all streams. So now we take this stream of completable futures to images that are in the process of being downloaded and stored and filtered asynchronously, and we get back a single completable future, which when all those things are done, will then trigger. And in that case, we've now got a stream of images, and we go ahead and log the results, and we keep track of the size. So again, it's very, very much like we did before. It just isn't using collect in the same way that we saw before. Instead, it's using this little helper method that kind of does what the finisher method did in collect, the join all stream method in streamutils, which is another helper class that I wrote. And once again, as before, we call join at the very, very end. And that's the one and only place where we really join in a blocking sense. Remember that the join all stream method we looked at before calls join, but this will never be a blocking join because you wouldn't get to this point unless all the completable futures were done. So this is just showing you that you don't have to use optionals. The control flow is a little bit more complicated if you don't use the optionals for the reasons we just saw, because we have to basically convert everything that would have been an optional to get rid of the empty optionals. That's what we do here. But once we've done that, then the rest of the code is streamlined and stripped down, and all the optional stuff goes away. So, of course, the interesting question now is, what's the performance implication of all these different things? So let's take a look at the examples. So we went ahead and ran all the different test programs, and there's a bunch more stuff here that we don't really care about because at the moment we don't really care about say the reactive streams version and so on. Let me just run this again just for good measure. It'll only take a second. And so we're going to take a look and see what the results are after we have run this. Okay, so there are two different types of downloads being done here. The first one is big images, and the second one is small images. And you can see that we have basically 14, I take it back, we have 7 big images and 7 small images. Interestingly enough, the completable futures 2 variant, the one we looked at just a moment ago, that performs the best for big images, followed by a reactor implementation, we'll look at that later, followed by parallel streams, followed by another reactor implementation, and completable futures 1 didn't perform that well, but if we ran the test again, it would probably do just fine. There's some variation in the test. But of course, the key thing to note is everybody's faster than the sequential implementation, right? Which is kind of what you'd expect because it's a lot slower. And then you look down here where we have smaller images, and CompletableFuture2 is still faster, but parallel streams is actually faster. They're actually the same performance. I'd probably need to have much more processing to really be able to generalize to anything. And once again, sequential streams performs the worst. Just for fun, let's run it again, see if we get the same results. We'll probably get slightly different results. And the reason we're getting different results, by the way, is we only have a certain number of images. And so you don't really see the benefits of this stuff until you have a lot of images. Now we get CompletableFutures1 is winning, followed by CompletableFutures2. And, so basically, the thing to come away with this from is you got to get your tests to run in accurate ways. But even that aside, completable futures are doing very well, which is what I would expect. Parallel streams are not doing poorly. Parallel streams are one heck of a lot easier to program than the completable futures stuff that we looked at. So if you're going to do this in practice, my recommendation to you would be first get the completable futures stuff. First get parallel streams. One more time. First get streams to work, sequential streams. Get your logic down, make sure you're getting the right results. If your performance is good enough, go off and, celebrate, go out, go to your, visit a sporting event, whatever you're going to do to celebrate. If your sequential streams version is not fast enough, try parallel streams. That should give you a speed up. If for some reason parallel streams still isn't fast enough to meet your requirements, which most of the time it will be, especially with larger multi-core processors like we have here, then and only then go ahead and try to do the completable futures stuff. And of course, what you should also realize here, and we'll talk about this more when we get into the reactive streams implementations, the reactive stream stuff is also super cool. And depending on the circumstances, it can perform just as well as what we're looking at here with parallel streams and completable futures. And some of this is also probably me getting smarter about things over time, right? So when I first did this implementation, I didn't know as much as I do now. So I should probably go back and redo these things. And I will before we talk about this for the reactive streams implementation stuff later. But the good news is pretty much anything you do will be faster than sequential. And that is the virtue of learning the stuff that we're covering in this course. You can take code that works, that's sequential, and then make it run a lot faster with almost no work by using parallel streams. And that's often good enough.